In section 5.4, day 1, we learned how to simplify radicals and how they are related to imaginary numbers. Before this year, you thought that we could never take the square root of a negative. What we learned in class is that you wouldn't get a real solution. However, the negative, when we take the square root, turns into imaginary, which is what I stands for. And then the square root of 81 is 9. So our answer here would be 9i. If you have a coefficient, leave the 3, turn the negative into your imaginary. The square root of 100 is 10, so we simplify this to 30i. When we don't have a perfect square, you have to break this up. We've got the negative out in front. You're going to have this that's going to turn into your imaginary number. The square root of 500 can turn into the square root of 100 times the square root of 5. This time the 100 is a perfect square, which becomes 10. With this negative out in front, I've got negative 10 I root 5, which would be my final answer. Same idea here. Negative 4 stays in front. The negative under the square root turns into imaginary number. This would turn into the square root of 4, square root of 7. The square root of 4 will turn into 2. The square root of 7 we leave alone. And altogether now, negative 8i root 7. In one of our study boxes here, we found the pattern using this information, but in order to just kind of get down to the point, I will become I, and that will be for all remainders of 1. Anything with a remainder of 2, because of the exponent representing the remainder, this will be for remainders of 2, and I squared will always turn into negative 1. I cubed related to a remainder of 3 will turn into negative I, and I to the 4th, which actually will be a remainder of 0, is simplified to positive 1. So here, you always want to take the exponent and divide it by 4. I showed the students in class, if you think back to long division and ask yourself, how many times does 4 go into 13? It goes in there 3 times, which would give us 12, and when we subtract, we get a remainder of 1. If there is a remainder of 1, we want to relate it back to I to the first, remainder, and the 1 and the exponent pair up. And so our final answer here would be I, coming from right here. Similarly, if we take 24 and figure out how many times 4 goes into it, it goes into it 6 times. In this case, there is no remainder. Since there is no remainder, it pairs up with I to the 4th, so our answer here would be 1. Even with larger exponents, we're trying to figure out how many times does 4 go into 3,251. First, we can figure out it goes into 32 8 times. When we subtract, we don't get a remainder. We have to drop our 5 down. 4 can go into 5 once. 1 times 4 is 4. This time we get a 1. We drop down our other 1. 4 can go into 11 twice. I'm going to bring this 11 over here. 2 times 4 gives me 8, and when I subtract, I get a remainder of 3. So the remainder of 3 pairs up with I to the 3rd, and my final answer here would be negative I. These would all be very, very similar. I to the 3rd, we said, turns into negative I. And when we have negative 10 out in front, negative times negative becomes positive. 10i is our answer. I to the 4th, we said, simplifies to 1. 22 times 1 is 22. So here you're just simplifying. I to the 4th will become 1, multiply it by 18. This will become 1, multiply it to 81. I squared turns into negative 1, multiplied by negative 8 gives me positive 8. In here, you're just multiplying negative times negative is positive 5i squared. We can simplify this to negative 1. 5 times negative 1 is negative 5. And the very last thing that we learned was FOILing. 6 times 6 gives us 36. 6 times 2i gives us 12i. Negative 12i and negative 4i squared. Positive 12i and negative 12i will simplify. The I squared turns into negative 1. 36 plus 4 would give us 40. Right here, rewrite 3 minus I times 3 minus I. Again, FOIL. 3 times 3 is 9. Negative 3i, negative 3i, positive I squared. This time they don't cancel out. We'd get negative 6i. This will turn into negative 1. Combine your like terms. 9 minus 1 is 8, minus 6i.